Hey everybody, I'd like to welcome you to the January 2023 edition of the Audio Programmer Meetup, and thank you for joining me. And I have some special guests with me today, Valerio Velardo and also Eric Tarr, and we're going to have some exciting topics to discuss today. Of course, we're going to talk a little bit about AI and ChatGPT. That, of course, is all the rage, and we've brought a domain expert, Valerio, who is the head of the Sound of AI YouTube channel to discuss it. And I can think of few people who are more qualified to talk about the implications of AI and audio and the latest breakthroughs and trends than Valerio. And then after that, we're going to talk a little bit about circuit modeling and Eric Tarr's circuit modeling library. So another really hot domain at the moment, or just in terms of audio programming, is how to take a piece of hardware and model it sensibly in software. And Eric has done a lot of work to make this easier, and he had a fantastic presentation at ADC 22 where he unveiled his circuit modeling library, and he's going to talk a little bit more about that. Before we get started, just want to thank our sponsors of the Audio Programmer Meetup, Focusrite and Sonox. Thank you very much for sponsoring the Audio Programmer Meetup, and without them, this wouldn't be possible. Also, you may notice that our co-host Rachel Locke is not able to join us today. Unfortunately, she's feeling unwell, but she promises to be back as soon as she gets better, and she has some exciting DSP material that she would like to unveil once she's back in the fold. And without further delay, we'll go ahead and kick into our first talk from Valerio. So he's going to talk a little bit about Prophet, which is a voice assistant that he has created for ChatGPT. And afterwards, we're going to talk a little bit about just what this space is looking like right now, and what Valerio's views are on the latest trends. So with that, I will pass it over to you, Valerio.
Okay, yeah, so first of all, Josh, thank you very much for having me here. It's always a pleasure to talk at the Audio Programmer Meetup, and yeah, to have like this very, very nice chats every time like with you. Yeah, so I'm going to talk a little bit about Prophet today, and then we're going to talk a little bit about the music AI space and some of the news. And there's loads and loads of interesting news right now. So regarding Prophet, so this is an application that came to my mind, I have to say, because of my childhood. So first of all, what is Prophet? Well, in 2 words, really, this is just like a sort of wrapper around ChatGPT. So it allows you to talk to ChatGPT instead of interfacing with ChatGPT through text. So you can talk to Prophet. Prophet is going to listen to what you say, is going to understand, hopefully, what you've just said, and then it's going to query ChatGPT through a library called RevChatGPT, and then it's going to use what you've said as a prompt to ChatGPT, and then some text is going to be generated. It just like comes back to Prophet, and then I use some text-to-speech sort of like library from Google text-to-speech to actually create a speech version of ChatGPT's response, and then you just like can hear what ChatGPT said. So in other words, I'm trying to turn ChatGPT into a voice assistant. Now, some of you like maybe wondering like what is ChatGPT? Well, I don't think like anyone really following like this meetup wouldn't know what ChatGPT is, but like in 2 words, this is a large language model AI system that's been trained by OpenAI, like the infamous AI company that's sort of like all the rage right now. And they used ChatGPT, they used GPT-3, 3.5 really, as a basis, and then they just like fine-tune it to have an artificial intelligence with which you can actually have a sort of dialogue. And it is extremely powerful. I've tried it, and I've tried it for a bunch of different things. So I've tried it to understand things myself, like quantum mechanics, or things that I didn't like recall because I wasn't looking at them since I was doing like my degree in physics, right? Or things like that. And it actually like came out like with answers that were really, really spot on. I've used it to ask it weird questions like what is creativity? So it's sort of like this sort of philosophical stuff. And it actually gave interesting results back, interesting thoughts, quite nuanced, quite articulated all around. So at that point, I realized, well, I've always had this childhood training, which is to talk to a non-human being, be that an animal or be that a machine, right? And now for the first time, I see a conversational AI that actually has some depth to it, right? While I was sort of interacting with it through text, I recognized for the first time that, I mean, there's really something here. So it's the level of like intelligence and knowledge that this AI is able to express is quite mind-blowing, I have to say. So, and as I said, this is a childhood dream because I've always been interested into not machine learning, but artificial intelligence and creativity since I was a child, really, right? And I think I was probably 11 years old when the big story about Deep Blue came out. And for the ones of you who are passionate about chess, probably that was like sort of like incredible milestone for human beings in general, for artificial intelligence in particular, because there was this match between the world chess champion Garry Kasparov, world chess champion of that time during the 90s. He was completely dominating chess, and this system built by IBM called Deep Blue. So they had a first match, and the first match, Garry Kasparov won. The second match, Deep Blue won. And that was an incredible result because 10 years before, 20 years before, it was just unthinkable to think that an AI system could actually beat the world chess champion. And so in a sense, like there, I started to have this big passion for intelligent machines. And later on, this passion for intelligent machines moved into passion for machines that can be creative. And indeed, with the sound of the eye, with my practice, research, and all of that, this is what I've been doing for like 15 years plus right now, right? So building machines that can be creative, especially in the music domain, right? And so, as I said, ChatGPT came out. I heard like all the buzz. I tried it, and I was like blown away by the result. Really blown away. And so I thought, well, this is probably the right time to hack together a solution and finally have a conversation with an intelligent machine, or more or less intelligent machine, right? And so that's what I did with Proverbs. So basically, I hacked together an application which is made up of 4 different components that allows me to talk, or that allows everyone who uses it to directly talk to ChatGPT. And for that, I haven't like built anything from scratch. Rather, it is more like a hack that puts together a bunch of third-party libraries that already exist for speech to text, text to speech, for audio playback, and all of this kind of stuff. So if you want, Josh, I can perhaps share my screen and guide you super quickly through the code, super quick. I don't know, like if this is something that you usually do.
Oh yeah, yeah. Please
Okay.
show us code. We'd love to
Okay.
see it.
Okay, so let me share my screen real quick. Can you see my screen?
Yep, you're all good.
Great. So this is PyCharm. So the application is built in Python. And So there's a main entry point here that is this run function that sort of like it's the entry level where you basically do all the different necessary things to interface with ChatGPT. So as you can see here, I initialize all the necessary objects, and these are all classes and wrappers around other third-party libraries like and tools that I use. And so there's one called speech recognizer that it does what it says, right? It's just like a speech recognizer. Then we have another object called speech synthesizer, Google speech synthesizer, because as I said, I use Google text-to-speech. Then there's an audio player. I instantiate that, and I instantiate ChatGPT as well. So ChatGPT is an object that allows me to interface directly with ChatGPT, which is relatively difficult to do, I have to say, because unfortunately, OpenAI hasn't released yet an API to interface directly in a handy way with the algorithm. Rather, there are a bunch of hacks and libraries online that do that for you, but there's a lot of like safe things on OpenAI's to circumvent, and I found this one library called a Rev ChatGPT, which works like a charm. Even though it has downside, which is it changes quite a lot because it has to be updated based on the changes that OpenAI, of course, brings to its algorithm and its interface, right? Okay, so here we just have like the different objects, and now we just enter the conversation loop, okay? So we are in a while infinite while loop. So initially we are in listening mode. So the speech recognizer listens to whatever you say through this like method transcribe. So you say something, you say like a sentence, and then we get the text prompt through the speech recognizer. Then after that, the next step is to send the text prompt to ChatGPT, and we do that through this method called getResponse that accepts this text prompt as an argument, and then we get the response. Of course, the response is in text format, so now we need to synthesize the text format into speech that then we can play back, and for that we use the speech synthesizer. So we just call speech synthesizer.synthesize, we pass the text response, and we get back the audio format of this text response. And finally, we just play it back. Now, to give you just a little bit more information about like the inlets that I'm using here. So let me show you speech recognizer. I can get in here. And as you see here, I use this library called speech recognition. This is a library that I really suggest everyone's using if they want to play around with speech recognition in Python, because it's a wrapper around a lot of very handy and powerful speech recognition libraries like Whisper, like Google speech to text, and many, many others, right? So this class is just a wrapper around speech recognition, basically, right? And I think here we use, let me double check here. I think, yeah, we use Google speech to text as default here. So that's all there is here in this class. Then if we go back here, you can see this other class called Google Speech Synthesizer. And again, this is just another wrapper around Google Cloud text-to-speech. And yeah, you can see this class has this synthesize method, but under the hood, we're just using this synthesized speech from the Google Cloud text-to-speech client. That's all there is to it. And then we have this audio player, and for playing back audio, yeah, this is super straightforward. I just use audio segment from PyDub. Now, I'm sure many of you will be familiar with this library, but if you're not, you should definitely check it out if you are a Python user, because this is super handy for all things music and audio processing. It allows you to add fade in, fade out, to segment, to manipulate audio like in many different ways. So yeah, remember to check PyDub out. It's a fantastic library. And finally, we have this ChatGPT, right? And as I said, this is a wrapper around RevChatGPT, which is this fantastic library that allows you to connect to ChatGPT. And you can find it easily on GitHub, and I think it's also available from PyPy. Yeah, it is available from PyPy because I have a TOML file here, and as you can see now, they've just released RevChatGPT version 0.1. Yeah, it's changing basically every day. Cool. So yeah, this is, as I said, like nothing really like fancy, but it is a nice story. It is a nice story that allows you like to have this impression of talking to a somewhat, I can't say sentient being, because of course ChatGPT is not sentient, it's not artificial general intelligence, nothing like that, but still, it's kind of a weird feeling having a chat with this non-human being, because it's very articulate, because the answers that you get make usually a lot of sense. They're very well made, the arguments make sense, and it's not just like, you know, sort of like dry answers that you get. It's a lot of like reasoning, pros and cons and things like that. And so with this little application, which by the way you can get on my GitHub account, so you can go to my GitHub account, it's called Music Alchemist, and there's one repo among many that I have on my GitHub account, it's called Prophet. You can clone it, you can install it with Poetry on your machine, and you can play around with it. The setup is a little bit convoluted because you have to set up Google Cloud text-to-speech, you have to set up as well RevChatGPT, which some sort of like session tokens and things like that, but I have a README that can help you just like navigate through this complexity. Now, yeah, I was saying, going back like to the sort of like goal of Prophet, as I said, it just like allowed me to have like these nice conversations with ChatGPT, and out of it, I also like made a video that I published, I think like yesterday on the Sound of AI YouTube channel, where I have this conversation with ChatGPT regarding all things like music creativity, machine intelligence, and AI, and the impact of AI on the music industry and this kind of stuff. And as I said, the answers that I got are quite sensible all around. I think I probably agree with 90% of what ChatGPT said. Apart from a couple of points which I cover in the video, but I want to mention one because that was a little bit hilarious, at least like for the people who are familiar with the music industry. So I asked ChatGPT, what do you think about the music industry and the advent of AI? Do you think the music industry is ready for this transformation? And ChatGPT said, yeah, I think more or less the music industry and the different companies are ready for what's to come. And I mean, if you've been in the music industry for quite some time, you know that that isn't necessarily the case, because I mean, the industry is built up with a lot of like gigantic and very traditional companies that have a hard time already doing some basic digitalization, let alone sort of like adopting AI solutions and machine learning. So yeah, that was a little bit fun. But again, if you're familiar with ChatGPT, you should also know that ChatGPT isn't a source of truth. Rather, it is a large language model. So it can say things that sound truthful, but they're not. So this is not at all surprising. But regardless, the majority of the answers that I got were particularly interesting. Yeah.
Fantastic. Thank you so much, Valerio. That was very awesome, and I'm excited to check this out. For the people that are tuning in, if you have questions, please feel free to list them in the chat. In the meantime, I've got a million questions, and I'll try to summarize those down into a few. So the first question that I have is more generally, what do you think this means for the future of search? Do you feel that because of course these are contrasting approaches between how OpenAI is looking to deliver information versus let's say Google with search and providing you with a list of resources that attempt to answer your question in the most accurate way. So where do you foresee that this is going to go?
Yeah, in terms of search, I don't see that big of an issue, at least for now, for Google. First of all, because as I said, ChatGPT or similar language models are not necessarily truthful, right? So you can't really trust what they say. It's not a search algorithm by any stretch of the imagination. So it's going to create things that sound plausible, but they may not be. And there are a couple of reasons for this. So first of all, the goal of OpenAI wasn't to build a search system, but just like a generative model. And the second problem that we have is that ChatGPT has been trained on a database of information, dialogues, and stuff like that exists until 2021. So ChatGPT is completely oblivious about everything that has happened ever since. It doesn't know anything, for example, about the Russian invasion of Ukraine, for example, right? So, and that doesn't make it as an ideal like search system. So, but, and there's a big but here, and the big but is that it may well be that in the near future, the goal of OpenAI or other similar companies will be to use this kind of technology with the goal of creating a conversational search engine. And that could be really cool. I think it's going to be a huge, huge challenge because it's difficult really to control sort of like the search and the search approach used by a system like ChatGPT, because it's just like generative, so you can generate whatever, right? And it's difficult just like to put filters and things like that because it's not simply searching through a database of items. It's completely different. It has this fantastic capacity to, which is a typical human capacity, and it's the pointer to intelligence, which is that of like looking at things and making connections and summarizing information coming from different sources, which is something that of course Google doesn't do. As you said, Google, all it does is just like tell you the things, the items that it thinks are the most relevant for your search, but there isn't any reasoning beyond that. So we are still at the level of information, not necessarily knowledge, where knowledge is the next step, which is, I argue, what ChatGPT does to a certain extent, which is just like extracting information from, extracting like all the most important like points from the information and creating connections. And at that point, we have real knowledge. But in the process, given the whole algorithm is generative, you may create a lot of noise and along with it a lot of like fake information that you may think is just true, because to you who may not be a domain expert for, say, for example, artificial intelligence or biology, everything sounds plausible.
And do you have any ideas or any thoughts on how OpenAI will look to iterate on this idea or on this problem that seems to be that it delivers the information as if it were true information, but in actuality it doesn't know whether it's true or not, and it could be false. Any ideas on where you think it could go from here?
I'm not positive that they will now look into that, because the sort of target application that they have is something completely different, right? So it's not, I believe, going against Google on their sort of like favorite like territory, which is like search, but rather doing other things that for which like ChatGPT or similar large language models are quite unique. Like for example, like taking text and creating like summaries like of that text, or helping you out like with creative input, or like turning like your sloppy prose into something that sounds a little bit better. of course, right? So in that respect, I don't think like that they will tackle this problem right now. And I think like their biggest problem will be that of understanding how to take like this amazing technology that they've built and turn it into a product that could target different sort of like strata of the market. So that for me like is their biggest challenge beyond the amazing technology that they've built.
Yeah. And speaking of turning this into a product or turning it into something useful, do you have any thoughts on what this will look like in the music space for us? Or how far are we from having a DALI or a ChatGPT that's specifically geared towards audio?
Yeah, absolutely. So yeah, this is something like that I've been thinking about like for quite some time now. But many of the people in the audience might have seen a couple of models, creative music AI models that have sort of like come out over the last couple of months or so. One being dance diffusion, and the other one being riff fusion, right? Like riffing in guitars, right? And they use this relatively novel technology used in image processing and image generation, really called like a diffusion model, and they adapt it to generate music directly from audio. Well, it's not really audio, but from like spectrograms, right? So they convert a audio time series, raw audio, into a spectrogram using a Fourier transform, and then they use that image and they interpret it, or like at least like to train the models as if like this audio file was just yet another image, right? And so refusion and dance diffusion think of music as an image, and they don't know anything about music, but they know quite a lot about generating images. So they see this spectrogram, which is just like a 2D representation of music or audio sound in general, where on the x-axis you have time, on the y-axis you have frequency, and then having like this 2D matrix, you also have sort of like the intensity of the energy for each beam that you have like at a given frequency and at a given time, right? And it just like generates more images, more spectrograms like this. The great thing about like this approach is that you can train the model passing also tags, right? So you say, okay, I have all of this music. So I have like some music by Michael Jackson. I have some music by Pink Floyd. I have some music by Chopin. For the music by Chopin, I say, yeah, this is classical music. This is in a minor mood. Or I don't know. For the music by Pink Floyd, yeah, this is progressive rock, or this is psychedelic rock, right? So the model not only learns how to generate music, but it also associates the different spectrograms that it receives with semantic descriptors. The great thing about this is that then when you are at inference time, when you are at generation time, you can tell the model what type of music you want. So I want some Pink Floyd music with clarinet, for example, right? And then the model should hopefully generate something that more or less makes sense. We have a couple of early examples with refusion and dance diffusion. The results are not fantastic, but they are super impressive if you think that the model doesn't know anything about music. It only knows about spectrograms. And that is like quite something I have to say. Now, there are loads and loads of limitations, and I see many of this. Main limitation is sort of like the duration of the amount of music generated, which is 1-2 bars, not more than that. You can chain a lot of like sort of like beats of music generated by the model, because all you do basically is you live like in a latent space, and you can sample points within a latent space that then get generated. So if you sample points that are close enough, then you tend to get like music that sounds basically the same, with slight differences. It could be like in pitch, it could be in timbre, it could be like in harmony, whatever, right? but they're similar enough. So if you chain music that's been sampled very close in the latent space, then you may get something that more or less makes sense, but it really doesn't make sense. And this is one of the biggest problems that we have right now in generative music, which is that at a very sort of like small scale, small resolution, we do things, we generate things that more or less make sense, but then when we zoom out and we try to look at the overall trajectory of the music, there we have big problems, because these models are not capable of understanding the overall musical structure. This is one of the big limitations that we have right now with DIP, generative music. And again, here we have to talk about like a distinction between two ways of generating music, one being audio-based or spectrogram-based, and this is the models like refusion or dance diffusion, and then the other approach, more sort of like conservative, and the one that I prefer, which is generating music from symbols. So using like a symbolic representation like MIDI, music XML, or whatever like a representation you may want to have. You have symbols and you manipulate those symbols rather than working with raw unstructured data like audio or spectrograms. Now, the other approach, the symbolic based, even with deep generative models, has the capacity to generate things that are a little bit more coherent at a larger scale, up to a phrase level, I would say, like say 8, 16, 32 bars, something like that. But even there's a big problem to go like to the next level, which is sort of like chaining together many phrases in order to create like a piece of music that makes sense and has ebbs and flows of tension. And for that, the only way forward that I say is combining together deep learning, machine learning on the one hand, and sort of like constraining its wilderness through symbolic reasoning and music theory. Unless you do that, you just have like cool toys that you can use as building blocks for sure. And for creatives, that is going to be like super cool. For example, if you can create small loops, small one-shots and things like that, but you're not going to be able to create entire pieces without injecting information about music theory, most likely.
Got it. So it sounds like a never-ending song.
Oh yeah, it
sounds
is.
sounds a bit like the source material.
Yeah, absolutely.
That sounds great. Um, and I was going to ask you what your thoughts are around the ethics of training a model on copyrighted art and data. I'm sure that's a question that's come up quite commonly, and I'm wondering if you have any thoughts on that.
It's a difficult one. It's a really difficult one. On the one hand, I think there should be some sort of acknowledgement for people, the artists, the writers, whose sort of like products a certain model has been trained on, for sure. On the other, I like to think about a parallelism between how we train a model and how we learn as human beings. If you take like a composer, for example, right? Say Schoenberg, right? Arnold Schoenberg. Okay, so dodecaphony, like beginning of the 20th century. So, and this Austrian guy was able to basically revolutionize the way we think of music. And in a sense, we can think of him as the father of contemporary art music, like very complex music, with a lot of theory, stuff like that. But if Schoenberg did what he did, it was because of the sort of like hic et nunc. So basically the circumstances, the context where he lived, and the music he had been exposed to at that point. There is no Schoenberg without the late string quartets by Beethoven, without Wagner, right? So in a sense, Schoenberg has been trained his whole life through exposure to some of these great artists of the past. And he's learned and he's internalized many of the the grammars used by like this fantastic artist of previous generations in order to create music that then was completely disruptive, right? But without like the history of contemporary or classical music, there wouldn't be any Schubert, because it's just like not possible now. And in a sense, I think like when we train a model, we do something similar, right? Because we're just exposing the model to a lot of music, to a lot of text, to a lot of literature, to a lot of paintings, right? Of course, the scale is completely different because we can feed billions musical pieces of spectrograms or paintings to a system like a diffusion model or ChatGPT, right? But and this would be like quite difficult for a human being to do. But in a sense, we're doing something similar, right? We learn from the past, and then we generate things based off what we've heard, what we've seen, and we use some sort of like recombination of many of those ideas, of concepts together to create something that hopefully will sound a little bit new. And so we just move the sort of like horizon of music creativity or music a little bit further because of what we've been exposed to.
Absolutely. Thank you very much for that. So we have a couple questions from the audience. So one question is, this is piping the results from one online service to a different online service. Do you know what the latency of the system is? I suppose that would depend on how many people are using ChatGPT at a time. Do you happen to know anything about?
Yeah, it really depends also like on the text input, right? So if you ask a question that is difficult, like for ChatGPT to reply to it, and it's going to take some time. But usually the amount of latency is comparable to the amount of latency or the amount of time that you have to wait when you are interacting directly with ChatGPT. So it takes time like to generate like the whole response, and it's the same thing for Prophet. Sending the information is really quick. Receiving back the information is super quick. The problem is the generation part. It can take like up to, I don't know, like 15, 20 seconds. Really depends on the question as well.
Great. We have a question from Togrol, who asks, do you think the closed box approach of AI makes people less curious about understanding and finding a mathematical or deterministic relationship in between facts? I'm not sure if I understand that question, but maybe you do.
Yes. So I think what he or she was saying is basically that the moment we start working with deep learning, machine learning, but especially deep learning models, like large models, we sort of like lose the deterministic understanding. So we don't explain things through equations or through like rules or stuff like that, but just like we use like super powerful statistics that does the work for us, and then we have a black box. We have no idea how that black box works, and we use it just because it works. Now, this is a huge problem, not necessarily in music generation, I would argue, because at the end of the day, yeah, we're talking about like things like that are within like the entertainment field, right? So there's most of the time people are not going to die because we generate some music and we don't know how that music has been generated. But for other application, knowing how a model has arrived at a certain decision or at a certain product is paramount. Think of medical diagnosis, for example, right? There are many systems that already work better than human beings at diagnosing, I don't know, like cancer, like melanoma or other things, but we don't know why and how. And that is a big problem. That is a big no-go. So in that respect, there's a whole chapter within the deep learning field right now that's called explainable AI. So they try to understand how these huge neural networks arrive at a certain decision through understanding like how the model works, and trying to convert statistics into something that is understandable for us, for human beings, into symbols that make sense for our brains, right? And that is one thing. But the question wasn't really that. The question was more about, but does the black box approach mean that we as humans lose interest in the mathematics behind the explanation of the world? And I would say, yeah, for many people, that's the case. And I've seen it happening time and again, because say for the majority of music tech or road tech companies that I consult, right? The thought is always the same. Okay, so we have this problem. We don't need really to understand how to solve it, but we're just going to throw some machine learning or some deep learning to it, and hopefully like that'll figure out by itself. This is a completely I would say like unsafe approach, I would say, for once. And then at the same time, I think you have to try to understand the world through mathematics and through things that are explainable as much as possible. And deep learning, black boxy approaches should be the last resort, right?
Great. And N. Dawson asks, with the exception of the ChatGPT call, are any other libraries making external calls from the code for profit?
External calls. Yes, there is one that does an external call to Google text-to-speech. Yeah. So you get back to text from ChatGPT, and then you send it to Google Cloud text-to-speech. Yeah.
Great. Okay. And it looks like that's all of the questions. If anybody else has any other questions, I'll give you a couple more seconds while I'm making this outro. Valerio, thank you very much
Thank you, Josh.
for that talk. Once again, be sure to check out his YouTube channel. It's really fantastic for AI and audio. It's called The Sound of AI. He also has a consultancy as well, that where he consults companies on all matters of AI and audio. And with that, thank you very much, Valerio. And
Thank you, Josh.
really appreciate you stopping by.
Thanks a lot.
Great. So while we're in this, and Valerio has to get going, it's a little bit late in Spain. So thank you once again, Valerio. Really cool.
Thank you. Take care.
Take care now.
Bye-bye.
Bye now. So before we go into our next talk, just want to remind you, if you're interested in talks like this and also the next talk that's coming up, be sure to join our Discord. It's a community. We're actually nearing 9,000 members now, developers and aspiring developers from all around the world who are really passionate about audio software development and learning how to code musical instruments and audio apps. You can join us on our Discord. The URL is theaudioprogrammer.com/Discord. Also, for anybody out there who is looking for contracting and job opportunities, we also have a recruiting service, and you can find out what jobs and contracts are available on theaudioprogrammer.com/jobs. And with that, we will segue into our next talk. So as I mentioned last year, I've known Eric now for a couple of years, and he's a professor at Belmont University, and we connected early on when I first started doing my Juice tutorials, and I was very humbled when he was telling me that he was showing some of his students the tutorials that I had been doing as a beginner, which was very humbling and really just motivated me to do more of it. So if I haven't told you this already, Eric, thank you very much, because that conversation was so motivating for me. And we've connected at various times through the years. Eric also teaches a lot of audio programming. He has a platform called Hack Audio. So he has a Patreon page where he's done workshops on circuit modeling and other tutorials using Juice. I caught his talk last year at the Audio Developer Conference in London, where he was speaking about his new circuit modeling library called Point-to-Point Modeling. And we struck up a conversation, and we had talked about how excited the community would be to hear more about this library and its uses. And the intent of this, at the risk of speaking for Eric, is to make something that's a very complex topic, which is circuit modeling in the audio domain, a lot easier for people who are looking to get into this. And so Eric's done a lot of great work with this. And with that, I will pass the mic over to Eric now to take over and to talk about this amazing library. So take it away, Eric.
Thanks, Josh. I couldn't have said it better myself. Thanks to you and everybody at whole team at the Audio Programmer for organizing these monthly meetups and streams. I think they're fantastic resources for people. And yeah, I'm really excited and appreciative of the chance to share with your community a tool that I've been working on developing for people that are making audio software, with the idea that in a lot of cases, people want to do things like create audio effects that are based off of hardware. So taking something like an analog circuit and being able to turn that into computer code and trying to make that easier and more approachable and accessible for just about anyone that would like to do that. So most of my presentation today is going to be just some demonstrations about how to use the library, but I will go through just a couple slides, background information about that as I switch over and start sharing my screen. And then we'll jump right into some code to look at. So I did share a little bit of this information already at the ADC, but for those, I guess that this would be new. The name of this library I've called Point-to-Point Modeling, and the goal of it is to do automatic circuit solving. So make it as easy as possible, having a computer do a lot of the work. And when I think about this tool and what I set out to do when starting to work on it, the goal was to really focus on analog circuit modeling and make it for everyone, whether that be someone that is already experienced with doing a lot of DSP stuff and just wants a tool to make their lives easier, or for someone that could actually care less about all the nuances of analog circuit modeling, and they just want something that already works and does a lot of the stuff for them and everything in between. So just to share a few more details about it, the particular type of circuit modeling that's included in this library is what's called component level modeling, or physically informed modeling, where what we like to do is be able to recreate the entire circuit from the beginning of the circuit to the end of the circuit and all the components that make up that circuit. We like to write some computer code that does what that circuit does. You can contrast that to this whole idea of machine learning and black box types of ways of learning how systems work. That's cool, and I've done lots of fun stuff with that approach to circuit modeling as well. But this approach is more about, all right, let's figure out, if you were to open up the hardware or open up a guitar pedal and look at what components are inside of that pedal, how do we do that? And, you know, I know that just to kind of address some of the things that people might think about initially with this is, you know, isn't that a complicated thing to do? You know, that's not a trivial thing to have to work on. And, you know, I think with this library, the goal is to say, yeah, I totally in agreement with that. And let's automate a computer to do that. You know, I have spent a lot of time in my own life studying circuits and learning the mathematics behind how you can model them. But even for me, like when I work on complicated circuits, it is actually easier and I get better results if I have this tool that automates the whole process, and there's less places for me to make mistakes in my own math when I'm doing it by hand and that kind of stuff if I have this tool that does the component level modeling already. So even for me, as someone that works on modeling, that this type of automation approach to it is something that I actually prefer myself. And you might also say, hey, I'm a kind of person that circuits aren't really my specialty. Maybe you're a person that focuses on the front-end developer, or you're a indie developer that's working on your own plugins, and you're expert at the graphics and the user experience and that kind of stuff, but you want some really cool DSP. Well, what this library offers, including the way of automating the circuit solving process, is that it also includes over 150 prepared circuits for you. If you were to use this library, these circuits are already made up ahead of time, and these are your classic circuits from all over the field of audio, from filters and equalizers you might find in a console, or like a preamp in a console, or guitar pedals and guitar amplifiers. And those kinds of circuits are ones that have already been prepared ahead of time and are there for someone to be able to use if they say, you know what, I don't want to have to actually worry about the circuit itself. I just want to have some cool DSP that sounds like analog stuff. This is what the library is capable of doing right out of the box. But if you're the kind of person that you are interested in circuits and nerd out on it like I do, the library has this arbitrary circuit solver, the ability for you to put in your own custom designs, stuff that's not even included in the library, as long as you use certain components, the common standard components of a lot of audio circuits. You can put those things in, and I'll show you exactly how to do that. The library will figure out the mathematical model for the circuit for you and allow you to easily just drop that into your software and be able to use it. So I think the best way to take a look at what this library is capable of doing is going through an example. And so what I'm showing you here on the screen is a circuit. This is about as simple or basic of a circuit as we might want to be able to ever use in audio. This is a low-pass filter. And this type of diagram is called a schematic. This is brand new to you. So a schematic describes the connections of a circuit and the components of the circuit. So in a circuit, we care about where the signal is starting out, the input of it. You can think of it like a guitar pedal, and where you plug your signal from your guitar into that pedal. And then we have an output to the circuit, and where we get the signal, the output jack of the guitar pedal, and send it on to do something else. And what we want to do is model that circuit that's inside of it. So it is the case that it's helpful to understand some basics of circuits, like the fact that our signal, in the case of an analog circuit, is carried as a voltage. And voltage is related to this other concept in circuits called current. And so some of those basic things are helpful to have an idea about if you're like brand new to it and you're trying to be able to get up to speed on even just using this library. What do I need to know to be able to implement some code? Maybe you're familiar with C++ code, and that's great. But in order to really get the most out of the library, it's helpful to at least have a foundation in those things. So this circuit then is made up of some components. We have a voltage source over here, is where our circuit or our signal is going to come in. Then we have a thing called a resistor with the abbreviation R, and we have a capacitor over here. That's an abbreviation C. They're just different circuit components, or what I also call circuit elements, as a way to distinguish a component, because a lot of people are using juice. Component is a graphics element, and so I don't want to mix up those terms. And so I call these things circuit elements, or resistor and capacitor. So the name of this circuit right here is called an RC low-pass filter. It is going to reduce the amplitude of high frequencies and allow the low frequencies to pass through. And so if you were to compare our output signal over here, the voltage that is across the capacitor here compared to the one at the input, it would be the case that the high frequencies have been filtered out. So this is the schematic, and really the main thing to understand about it is to be able to recognize what elements are part of it, and then also where those elements are connected. And in a circuit, the connections between elements are called nodes. And so you need to be able to recognize where the nodes are going to occur, and those are the places, the points of wires in between the components. So here we have a node. I've numbered them already. We have a node over here. I've just said this is node 1 between the voltage source and the resistor. This is node 2 over here between the resistor and the capacitor. And in the circuit, there's usually a reference node that's called ground. A lot of people have heard of ground because it's a point in, like when you plug into a power outlet, there's usually a prong in your connection that goes on and connects your plug to ground. So these are things to be able to recognize in a schematic to then be able to use a library to be able to turn this into code. And so on the next slide, that's exactly what I'm going to do. I'm going to show you as a developer, if you were to use this library, the extent at which you need to be able to look at a schematic and then how to take that information and put it into code that then can be turned into software, a plugin or an app or any type of C++ software that you would want to create. So over here is a class for implementing this RC low-pass filter. And so the way that the library works is you inherit from this generic thing called a circuit, and you then give your own unique name to the circuit that you're trying to create. So this one is a specific type of RC low-pass filter. It's a first order one, and it's passive. It doesn't amplify the signal. It doesn't have like an op amp to it. And so this is just the name that I've given this particular circuit. So in the constructor is really the only thing you have to specify in order to translate this schematic over to some computer code. So in the constructor of it, what you're going to do is create something called a layout. The layout is essentially the schematic of the circuit. And so you're going to specify the number of nodes that are included. So over here we have 2 nodes other than ground. So we have 1 and 2. So that's the number of nodes. And we have to say then where the circuit elements are connected and add them to our circuit layout. So we have a voltage input. We need to recognize where that is. And the voltage input goes from node 1 down to node 0. So it connects up here to node 1 and goes down here to node 0. Then we have the voltage output that connects from node 2 down to node 0. So we need to specify where that's going to be. And then we can put in our circuit elements. So like our resistors and our capacitors. And because this library is capable of handling an arbitrary number of resistors and capacitors and other elements that are part of it, what we do is we create the single instances of those resistors, and then we add them to a vector that goes into our layout. So you could have 1 resistor or you could have 10 resistors. It's really up to your circuit for how you put them in. So a resistor has some value in ohms. So that's the unit of resistance. And in this case, I have a resistor that has 4,700 ohms is its value. And then it connects from node 1 over to node 2. I take that single resistor and I put it into my vector that goes to my layout. Do the same thing for the capacitors. So capacitors have units of farads. So this is nanofarads. 47 nanofarads is the capacitor right here. And even though I didn't include it on my schematic, if you were to go out and look for audio schematics for your favorite kinds of circuits, they are usually going to give you the values of the elements in it. So you say this resistor has this value and so on. So this capacitor goes from node 2 down to node 0. We put that in our vector, and then we take the whole layout and we pass it into this thing called a circuit model. And that's where the magic of the library happens. All the DSP is part of this thing called a circuit model. And now you can use this class that you've created as the effect, as the DSP of a plugin. And so let me switch over to an example of this and show you how it works. So I've got a Juice project already prepared, but just for, because I'm to be comprehensive, this doesn't necessarily have to be used with Juice. I just know a lot of people that are doing real-time audio signal processing are already using Juice for plugins and apps where I think that this might be used, but any place where you would want to do C++ real-time audio processing, this library can be used for that. Okay, my Juice project, I have this thing called this passive first order RC low pass filter. And I've put it into this file that I've called my circuits as just a place where these circuits can exist. And then I also have other ones in here too that we can come back and take a look at. So just other examples of circuits that are included. And then to be able to use this as part of your library or as part of your plugin, over here, we just need to include that file and say, there's some circuits that exist over here that we want to be able to use. And then we come down here and we create an instance of that passive first order RC low pass filter. So we create an instance of it and we call that our effect. And then in our implementation file, we go over to prepare to play. And in prepare to play, we just call effect.prepare. And we pass in the information for our effect to say sample rate and samples per block. And then we can come down here to our process block and we have an effect that we can use. And we grab the channel data from our buffer. We pass that channel data into our effect using this one called process in place. So that is going to take the input audio, process it with our circuit, and then put it back on our channel data to be able to use. And then we also need to know the number of samples and what channel that it belongs to. And if you do those three things, create an instance, prepare it, and then add it to your process block, you've got a circuit now that you can build and run in a plugin. So hopefully I went through that very quickly, but that's the steps. Those are the steps to make it work. So I'll go ahead and I've got this set up to build and load up in Logic and show you this low pass filter in action. So this will come up in a second. And what I'm going to demonstrate how it works is with just taking some white noise and putting it through the plugin. Since this is a low pass filter, you'll be able to see that the high frequencies of the white noise get reduced in amplitude if you look at it on the frequency spectrum. So let me show you what I've got here in my session. So here's the input signal, the white noise that I'm displaying on my frequency spectrum plugin over here, the span plugin. And then I have the circuit that we built is for this one right here, the point-to-point one. And this is a particular version of it, the light version, which I'll explain the differences between all these things here in a second. And it's bypassed right now. And if I add this one in to the signal chain, you'll see that we get our low pass filter and reduces the amplitude of high frequencies. And so we have now done the modeling of this particular circuit. And if we were to put white noise through a resistor and a capacitor like this and measure the output, we would get this same type of frequency response to it. So it's doing the effect of what would happen if you had these elements that you connected together and were able to simulate that. So that's the process for how you could do this. And as a developer, I can go back and show you some more things here included. So this is a very classic kind of circuit. You know, you would see this circuit as one of the first ones if you were ever to go out and learn about, you know, how circuits work. This is one of the first ones you would come across this type of low pass filter. So it's very useful and a good place to start. But there's also ways that we can build off of that and have other types. And so the whole circuit library includes many, many, many circuits involved in it. So here's a low pass filter. Here's a high pass filter where these things are already added in. Here's one called an active second order low pass filter. So active means that it has some amplification to it. It has a thing called an op amp. So up to this point, I've just been demonstrating circuits that have resistors and capacitors, but this library also includes other elements like an op amp or operational amplifier, which is another important building block to a lot of audio circuits. and other elements too that I'll cover in more detail. So if you were the type of developer that said, I know that I want to have analog circuit DSP in my effect, but I just know that I just want to have a bandpass filter or a high pass filter. You just have to look up the names of the ones that are already included and then just come over here to your plugin processor and swap it out and say, let's have a passive second order bandpass filter and rebuild the plugin. And now we have a passive second order bandpass filter instead of the other one. So it's just a matter of swapping out the name of the class or the circuit right here to be able to get all these other different types. Just some other examples. So we have circuits that are based off of a lot of guitar pedals. So if you're familiar with the Big Muff is a famous guitar pedal. You have the tone section that's modeled in there with some resistors and capacitors in it. So those are just a few of the many options that are included. So let me take a step back and then talk about the different versions of this library. So the technology itself I've called point-to-point modeling that then can be used in different ways or with different versions of the library. So where you can find this and be able to use this library is off of my website. So I maintain a website called hackaudio.com. And on here, you can find a link to point-to-point modeling. And from here, there are a couple of different GitHub pages available where you can access this. So the one that I've been demonstrating so far is called the Lite version, the LT. And this is non-commercial. It's a free version to use, and it's publicly available. You can go anytime you want over to this GitHub page and download the library and the example juice project that I've been showing you and be able to use it and just open it up and build it right away and be able to use it. So it is a light version. It doesn't have everything included. It doesn't have all 150 circuits built out ahead of time. And it also only includes a limited number of circuit elements. So resistors, capacitors, and op amps, and voltage sources, and those kinds of things. There is a commercial version of the C++ library that's intended for people that are releasing commercial software on it. And that includes resistors, capacitors, op amps, and then it also includes variable resistors. So things that are called potentiometers that allow you to have parameterized control over circuits. Those are the typical ways that if you want to have like an equalizer where you change the frequency or change the amplitude for those things, you need a potentiometer or variable resistor to be able to do that. But then the commercial version also includes nonlinear elements. So things like diodes, which are used in clipping, distortion for a lot of guitar pedals, and even some guitar amplifiers. So you can build circuits that have diodes, transistors, in particular, a specific type of transistor called a bipolar junction transistor, which has two different types based on the doping of the semiconductor inside of it. So there's ones that are called NPN and also PNP, and there are both types of those transistors included in the library, commercial library. And then also a vacuum tube. So a lot of circuits that people love, analog, cool sound, saturation, distortion, that kind of stuff comes from vacuum tubes. And so there's a model of a 12AX7 that's included, probably the most widely used, well-known vacuum tube that can be added to circuits as well. I'm going to demonstrate that here in a second on it. So if you are interested in the C++ commercial version of the library, what I would ask is that you would just contact me through the website, and I'd be happy to talk you through and get you set up on being able to do that on there. There is also a MATLAB version that I'm going to demonstrate next. And the thing about the MATLAB version is it's not really set up, because it's MATLAB, if you're familiar with that, to release real-time audio signal processing software. And so what I've done is created the full version of the library as MATLAB code that you can use and be able to prototype your effect and get familiar with how it works. So the MATLAB version uses MATLAB and it uses MATLAB syntax, but it's all structured in a very similar way to the C++ library to be able to use that. And so if you are interested and you're familiar with MATLAB or willing to work with it, the MATLAB version includes resistors, capacitors, diodes, transistors, tubes, and everything else as part of it. And it also includes some scripts for how you can test out your own code and look at common things like the waveform and the frequency spectrum and stuff built in so that even if you're wanting to work with the commercial C++ version of it, MATLAB is going to be a super fast way to prototype it and figure out, all right, is this circuit working? Does it have the frequency response that I want? Do I need to change the value of this resistor, this capacitor to something else to get different results and that kind of thing? So you can get the MATLAB version of it. This one is free and publicly available as well. I'm a teacher, and so I think that other teachers that are using MATLAB already, this is a tool that for you to be able to use. So let me switch over and show you what the MATLAB version is all about, and then I'll show you some more stuff about the demo with the C++. So with the MATLAB version, the idea is to make it very similar. So here's an example of a circuit. This is an active second order low pass filter. And in MATLAB, when you do inheritance, you do it this way. When you declare a class, we have a constructor, and then we do the whole same thing as before. So we have a layout, we specify some number of nodes, we set what the input and output voltages are, we declare the particular types of resistors we want to use and their values, and we put those into an array that goes into our layout. We find our capacitors, we have our op amp. So the whole thing in MATLAB, even though it uses MATLAB syntax, the whole structure of it is very, very similar to what you'd find in C++, to make it easy to go between one and the other and test out your things that they're working. Included in the MATLAB version of the library, if you were to go and download this on your computer right now, you'll find a script in there called test script. That's the easiest one to just open up and get started being able to use. And so the test script is really for prototyping, where what you would do is go in and find some particular types of analyses and say, all right, I want to look at the waveform, the output waveform, or the oscilloscope is how it would be looked at if it were analyzing a circuit. We want to look at the waveform, we want to look at the frequency response, or the total harmonic distortion, or the DC sweep. These are the common types of analyses that you would look at for a circuit and see if it's behaving correctly. So just to show you some of the nonlinear types of the full library, here's one called a tube clipper. And this circuit is one that's based off of a journal article from the DAFX conference. I can show you what this circuit looks like, give you some context for it. So here's a circuit, a schematic that we like to be able to translate into some code. So the main new thing here is this component of our circuit is our tube. And so it has some specific nodes that it works off of, one that's called the grid, one that's called the plate, or also the anode, and then one called the cathode. And so those are the nodes we need to be able to describe, 3 nodes in this case, for our tube. And then over here we have our input voltage, we have some resistors. Over here, we have a voltage source that is up here at the top of 150 volts. And we'll take our output voltage from this circuit up here by the plate of the tube. So that's translated over here into our computer code with some resistors, a model of the 12AX7. There's actually 3 different versions of a 12AX7 included in the library. You just need to pick which one you want to use from different manufacturers. Put that into your layout, and now you have a circuit that you can use. So let me run this. And what we'll see here, the way that I've set it up right now, is that it's going to display the input and output waveform. So this is just a sine wave as our input signal. And we'll see the result of the processing, that there is this cool tube saturation happening. So yeah, our input sine wave is actually relatively small, and this is a tube amplifier, so you're getting this huge increase in amplitude that has this asymmetrical distortion. And so this is really one of the cool parts about analog stuff that unless you do like that component type modeling where you are modeling the actual elements, the tubes and the resistors and how they interact with each other, it's very difficult to like write an algorithm strictly just from digital signal processing on its own without the physically informed modeling that would give you something as cool as this kind of saturation. So again, fairly easy to look at a schematic like this and recognize the elements. Here's, we have a voltage source. We just number these things as this being node 1, node 2, node 3, node 4, connect the things to it, and then be able to do the processing of it. So yeah, the MATLAB script, very similar. We just need to prepare the circuit, and then we do a process of the circuit in here, along with synthesizing the input signal and then plotting it. I'll quickly show you another circuit. This is our active second order low pass filter on it, and we'll switch this over and look at our frequency response instead of our waveform. And here is our resonant filter. So you can see that there's some bump up in increase in amplitude. This is an active filter. And you get this cool analog, resonance thing happening that, then could be parameterized and swept around and control the resonance and that kind of stuff. So if you're like a software developer that makes synthesizers, the idea is you could have a really cool analog modeled resonant filter that you add onto your synthesizer and be able to use fairly easily without having to do a lot of the modeling yourself. So that's some stuff about using the MATLAB library. Again, the MATLAB one is free and publicly available. You can download it now off my GitHub page. It includes all the components of the commercial version of the C++ one. So it's really great for prototyping and being able to do that. So last thing I'll cover and then open it up to some questions is to show you what the example juice projects are like and get a more of a background idea about what the library is, what the library includes. So let me jump over here to the juice ones. I have these two juice projects. This is the light version of it, and this is the commercial version that has more of the circuits included in it. So the main thing here is we have some header files that are included as part of the library, and we need to link to those right here. And then the actual library itself is a static library that just needs to be linked in here, and then you can go ahead and automatically use it in the Xcode project when you open that up. So here is the, let me pull up the other one to see that. So you have Mac and Windows, you have some header files for the circuit and then the circuit elements. So here, this one has all the circuit elements to be able to use the resistors, the capacitors, and the op amps. Those ones already laid out. And then the header to the implementation file for the library, that circuit model thing that I talked about where all the DSP happens is inside of there. And then we have the base class of our circuit that we inherit from that has those common audio callbacks like prepare and process a sample or process in place or process a buffer. And you have pointers to the inputs and outputs. So I try to make this as standard or flexible as possible. You can certainly use it with juice, but you can also use it if you're not using juice types and you just have buffers, you have a pointer to that buffer, you can very easily tie in these things. So the library is really set up if you're trying to do real-time audio processing to do it either at the sample level or at the buffer level by using these particular callbacks that you can then use with any circuit that you inherit from here. The full version of the library includes Very similar kind of stuff with the addition of some more circuit elements. So in here we have variable resistors, we have diodes, and lots of variations off the diodes. So if you're familiar with diodes, there's particular types like silicon diodes, or the old ways you'd find in guitar pedals were germanium diodes. So we have models and choices that you can select between those ones. You have different types of transistors. The BJT transistors are in here. And then also the variations off of the tube, and being able to do those. Let me show you then in, I guess, real time here, and then I'll open it up to some questions. I have this other Juice project prepared over here with the full library, and let me show you. We have it set up right now. Let me pull up the tube clipper to be able to use here, and also show you all the circuits that are included. So this one has, the 150 circuits that I've talked about, and you just have to type in the name of it right here to be able to use it. We have different ones from guitar pedals. This is a Boss guitar pedal. This is Ibanez guitar pedal. Ones that are already built out and ready to use. So there's tons and tons of different options that each are going to be unique. Vox pedal, and so on. So classic filters, these are your low pass filters, high pass filters. There are ones that are specific to audio, so Baxandall ones. If you just drop in a Baxandall tone stack, you can easily do that. Many different ones. Amp tone stacks. So here we've got circuits that are based off of Marshall amps and Fender amps, and very boutique kinds of amps, Vox tone stacks. So yeah, stuff that if you're just looking for things that are already prepared and built out ahead of time, a Marshall Blues Breaker tone stack, those things are already examples that you can also check out and say, oh, what are some other ways, things that people have done. So let me quickly build this one and show you the tube clipper running as a plugin inside of Logic, and then that'll be enough for my presentation, I think. So again, if you're interested in this, check out hackaudio.com, and feel free to get in touch with me there. Interesting. I think I was already running a version of this over here, which may have been the issue. Pull up the sine wave down, and so this other version of the plugin is the one that includes the tube model in it. So let me stop running this from the other one. I think that caused the problem. Try it one more time. So with this one, I'm going to put a sine wave in, and we'll see initially that the sine is just a single tone, and then we'll run it through our tube clipper. We get that cool saturation. We'll get some harmonics that we see on the spectrum to be able to see there, to see it working in action. All right, so I'll switch over to the sine wave. Start down initially. Turn on our tube model. And as we turn up our input signal to our tube, now we're starting to get the saturation. And I guess to compensate for that, let me turn this gain control on. Bring it down. It's over here. All right, so this is post gain, so we can see the saturation happening, but then also make sure it's not clipping when it goes into our hard clipping when it goes into our analyzer. So there's our tube clipper running in real time, based off of that model from the paper. So you can see some examples of both linear circuits and also nonlinear circuits if you're looking for that type of analog saturation to add into your own tools. So I think with that, I will stop sharing my screen and see if there's any questions or further discussion about the library.
Plenty of questions. So the first question, which I told them the answer is probably yes. I imagine I can't really think of why this would be no, but could this be used on a compressor circuit?
Great question. So it depends on the compressor circuit. One of the limiting constraints right now with the library is that you can only create circuits that contain these particular kinds of circuit elements. So resistors, capacitors, op amps, I've listed all those out. If there's a compressor circuit that just includes those circuit elements, then yeah, it will work on arbitrary circuits. Now, sometimes there are circuits that are really, really complex, and this circuit library with MATLAB, at least, when it's not trying to do it in real time, if you put in a circuit that has 100 nodes and 100 different elements, MATLAB might process the data overnight and give you the result in the signal the next day on it. But it will just come down to your computer and its ability to be able to process something as complex as a compressor. Now, I'll also say, as someone that has been using this library already a lot, is that a lot of compressor circuits will do things like have a special type of op amp that has a special input where it is basically the input voltage is the control voltage, like the VCA, right? It has to be an op amp that can handle a VCA input. And the model of op amp that I've included doesn't have the ability to specify a separate voltage input to be able to modulate the amplitude of the op amp. So if you come across a circuit that requires that, then unfortunately right now, that's not possible. But I can say that I already have plans and I've already started to work on adding more components or elements to the library that will be updates in the future. So right now, it just has the ability to do the ones that I've listed out, but already in the pipeline, I'm working on different types of transistors. So a JFET is another type, and a MOSFET that you'll find in a lot of circuits. I'm working on a model for a transformer to be able to be included there, because a lot of people like transformers, and some other ones too. So yeah, I definitely have plans to add in new models of op amps, but there's kind of just like only so many hours in a day to be able to add stuff and try and build out something that kind of works with a certain subset of elements. And then hopefully over time, I'll be able to add to it and make it possible to make more and more kinds of circuits. So appreciate your interest in doing that. And it probably just comes down to whatever circuit a person is looking at.
Great. I'm pretty sure the answer to this question is no, but Oliver Moore asks, does this lib have oscillators? If so, which ones? So this is individual components and not oscillators, which would be a collection. Am I right in saying that?
Yeah, that's a great question. So at the moment, the circuits that I've focused on are audio effects. However, that's another big thing I already have on my list, my whiteboard of next things that are going to come up are going to be how this could be used more for synthesizers, for people that want to do that, and creating, resonant circuits that generate a tone and be able to do that. So again, a lot of times that comes down to like the model of the op amp and having an op amp that can go into some mode of self-oscillation to generate a tone. And so that's something that I need to add, but definitely is in the pipeline for stuff that I want to include and make this library, expand it from just, kind of your standard classic audio effects to now being able to do more things, including cool analog synthesis.
Fantastic. Studio Devil asks, what type of solver is being used? fixed time step, state space representation, explicit or implicit method?
Yeah, great question. So I have done all kinds of different circuit modeling, and I teach a class at my university that we go through all the standard types of things, including state space, traditional Laplace transform, bilinear transform methods, modified nodal analysis, and like a decay method, that's discrete Kirchhoff method. Also other ones that are out there like wave digital filters for doing component level modeling. And I can say that this library comes from kind of the more traditional types of circuit analysis on it. So not wave digital filters, but what I've done with it is over the years of implementing different methods for circuit analysis, I've taken bits and pieces from state space and modified nodal analysis and the decay method and all these things. And I have kind of come up with my own approach to modeling that is based off of those things, but not the same as any of those things. And so that's why I've called it point-to-point modeling, is that it is like a different approach that is not found in the literature or described as any of those other types of approaches. They are, I think that there are, benefits to all of them. And so like, we're trying to do something in real time that is efficient and all this kind of stuff. I've pulled lots of ideas from state space and modified nodal analysis and decay method and the Laplace transform. And I've kind of put those all together to do something that isn't any of those things, but is also similar to those things, I guess, is for the person, sounds like they have some experience with it. That's, I guess, what I can share about the actual mathematics behind it.
Okay. I guess that answers the next question from the same person who asks, is the source code of the circuit solver code available to review?
Yeah, great question. At the current time, it's not. It is included as a compiled library. And so that is what I consider my secret sauce of what I'm trying to offer onto people. And I am also, if someone is interested in learning circuit analysis stuff, I have tons of resources. I have, a whole YouTube playlist of classes that I've taught that go through all the different traditional methods of circuit analysis. And I would be more than happy to communicate and share that with the community and say, all right, if you're interested in actually learning how these different techniques work, I can give you, video lessons and lectures that I've done for my classes. Just share those publicly for anyone that's interested in actually getting into it and learning that themselves.
Great. Farida asks, a tall order, but is there any kind of parsing method or feature to visualize the circuits you've implemented?
Great question. This actually was something people asked at the ADC conference as well. And at the moment, I have not worked on that. Supposedly other people have worked on it already to kind of do a similar thing. There's software out there called Spice, where you actually have this graphical method of laying out something that looks like a schematic. But I have not put time and energy into doing that. And I actually have that as a lower priority at the moment for stuff that I would want to work on. For me, trying to add in more circuit elements and make it possible to do more types of circuits is kind of what I am focused on. But yeah, I also agree that that's really cool. And it would be nice to be able to take all this code and be able to automatically output on stuff. But maybe if there's someone in the graphics person in the audio programmer community that wants to talk with me, I would love to speak with them about doing this together.
I'm sure there are some people that'd be happy to help. Studio Devil also asks, can components be adjusted in real time, like potentiometers or values of capacitors?
Great question. So the potentiometers are set up to be adjusted in real time. And in fact, there's a bunch of stuff built into the library to automatically do the smoothing of parameters. So that's something that comes up, and really the smoothing and that kind of thing has to be handled closely to the DSP. And so even if someone wanted to, do their own smoothing, I think it kind of makes the most sense. You'll get the best results by using the built-in smoothing as part of the library. And so in the full version of the library that includes potentiometers, there's a callback function where you can set like how often you want the smoothing to happen and be able to adjust things. So, you can, use more CPU and have the smoothing happen more quickly, or over time, less CPU and have longer increments in between those things. So yeah, the library is meant to be parameterized around these variable potentiometers. Now, in real time, I don't have the ability to like change values of capacitors, mainly because I've tried to stay true to like what you can and can't do with a real circuit. There's not like a type of capacitor that's common that we would use, or like a transistor where you're like changing the values of those things. And so most things are parameterized around these variable resistors on it. With that being said, the library does allow you to set these things ahead of time. And so there's actually a lot of control for many of the more interesting kinds of elements to be able to set them. So yeah, you can set the value of a capacitor, but then like for a transistor, you can set whether it's a NPN or PNP type of transistor, which you'll find in different circuits. You can set the type of semiconductor that's used. So like a silicon or a germanium. You can set these common types of parameters that you'll find in like a model for a transistor. There will be things like a saturation current or a emission coefficient, or like the quality, or those kinds of factors. If you're familiar with like those things that are associated with transistors, those are things that I've exposed as part of the model for them. And you can go in the constructor and set, I want to have, saturation current of whatever you want, as long as it's, ends up with a reasonable transistor, you can change all those things. So there's a good bit of control, I guess, where you might think of it typically happening in terms of variable resistors and then the values of all the elements, and try to make, those things that for people that want to tweak and, mess around and find out what happens when you change the value of a vacuum tube to something else, or, change the diode to some other value. You can tweak those and find out and learn about the results, or get unique and different results than anybody else has ever done before.
Fantastic. Gunnison asks, do you have a hierarchy of circuits? Not
Hierarchy of
sure what,
circuits.
I'm
I
not
guess
sure
I
what
have,
they mean.
the organization of the circuits right now is kind of based on like where they're commonly found. So like there's stuff for like guitar pedals. You'll find like guitar pedal tone circuits and guitar pedal clippers and guitar amplifiers and preamps and tone stacks of a lot of guitar amplifiers, and they're like organized around those kinds of things. Then we have like a bunch of circuits that I would just call like analog clippers. So like all these things, it's maybe not a guitar amplifier and it's maybe not a preamp to a console, but it's like a classic circuit that we could just use for cool analog saturation of stuff. We have a bunch of those, and then your analog filters, so Baxandall and Salem key, and your standard audio ones. We have like stuff based around like, all right, if I'm looking for a filter, I can pull up this folder or this file and find like 20 different filters, high pass, high shelf, whatever, and be able to find them that way. I guess is how it's organized if you were looking for a particular thing.
Okay. Kostas asks, does the MATLAB version depend on any additional toolboxes?
No. So it only just requires the MATLAB main library, or the MATLAB software. And I guess it uses, I don't even think the test script just uses a sine function. So it doesn't even require like the signal processing toolbox, but a lot of people have the signal processing toolbox. So you could, swap out sine function for square function and put in a square wave, but you don't even need to do that. You could just use the MATLAB one and then the code that I've created for it, and that would work in and of itself.
Right. Leon asks, with the MATLAB being completely open source, can't you just use the C++ export in MATLAB to export the circuits?
Great question. So I don't know if you try to export it to turn it into C++, if you would have good results with that. I haven't tried it. I actually wouldn't have a problem if someone wanted to try it and see what happens. I do have, a license associated with it for personal use, that if it was for personal use, have at it and see what happens, but don't violate the license, I guess, is what I would say.
Great. Togrul asks, are the currents and voltages calculated depending on sample rate, or is there any oversampling in the calculations?
Yeah, so the library also includes some built-in oversampling on it, and that's something that I'm also working on giving the developers more control over, on trying to find out a good way to do that, so that because I know that it's something that people want to be able to, okay, it's taking up too much CPU, or I want higher sound quality and be able to control that. So yeah, there is oversampling that's included in it already. And just like the parameterized smoothing control, the oversampling kind of works best when it's at the library level. And so I've included it as just native oversampling code right into the library itself.
Great. Metafunction, aka Phelan, hi Phelan, asks, is the non-linear stuff Newton Raphs using the Newton-Raphson method?
So yes and no. It's another kind of thing where it's based off of the Newton-Raphson method, and then there's some tweaks to it that I've done that are trying to make it smoother and also faster and less prone to instability. So it's a iterative solver derived from the Newton-Raphson method with some of my own tweaks to it.
Great. Sam Schaefer says, great talk. Question for nonlinear circuits. Does the C++ implementation guarantee convergence? If not, are there safeguards to prevent it from hitting infinites or not the numbers, things like that?
Yeah, there are definitely some safeguards that are in there. I'm still calling the version of it a beta version specifically for this reason, that I'm, adding as many of these nonlinear circuits as possible that I know are working to the library as examples of ones that people will have. But at the same time, I can't guarantee 100% that every single possible circuit and every single possible input signal is going to work. And so there are some things that, like, if the circuit went unstable, it would reset and carry on from there. But it's the type of thing that I've tried everything I can to address it with many of the example circuits that I've been working on with it, and would love to work with another developer that if they had ones that they were working on and they came across something, I'd love to be able to improve the library to make it more robust and handle as many as possible.
Great. Two questions that are kind of related from Darwin's and Matthew Hill. One is about CPU usage. I know this may be difficult to say, but how many instances for relatively complex, interesting design on a modest computer like an M1 Mac? And then Darwin's had asked about if the library would work on an embedded chip.
Yeah, so this really depends on the circuits that you're trying to implement and then your processor on it. And there is a huge range of of CPU usage that you can have with this. From relatively simple linear circuits, you could run 1,000 instances almost of this probably on it, like a Mac Studio, because it's just so lightweight and for certain types of circuits. And then you could have other kinds of circuits where you're like, honestly, I could probably put one together in 5 or 10 minutes that wouldn't run on my Mac Studio, because it just has multiple nonlinear elements and too many nodes. That's just a reality of trying to be able to do, an arbitrary circuit solver, is that it's not too hard to put together circuits that are just not capable, or our computers aren't just capable of handling right now. I hope in the future that computers continue to get faster and faster. But for like a lot of the common circuits that we find in audio, they can be implemented and will run, just fine on a person's personal computer. I can say that in my own experience, like working on guitar amplifiers in particular on it, I usually do things like break up the circuit into multiple stages. And by doing that, you go from having a circuit that won't run on the computer to now having, you've broken it up, and that isn't exactly true to how the circuit actually behaves in real life, but it also is not too far off from kind of the independence of these different stages of a guitar amplifier. And by doing things like being intentional about where you break up the circuit into multiple parts and treating them as smaller things, with each of them maybe having 5 nodes rather than having a gigantic circuit with 20 nodes, then there are choices that you can make as a developer like that will make it possible to implement even circuits that have tons of components and tons of nodes, if you are just familiar with how to do some of those common types of things that, even if you weren't, if you were doing this all by hand, you would probably make those similar kinds of choices anyway on it. So hopefully that answers the question.
Great. So there's another question that's sort of around the same realm. What audio equipment do you use to evaluate the theoretical code that you're creating? How audiophile-ish are you while listening and comparing results? And thank you for the inspiring live stream.
Yeah, great question. So in some cases, I just take a schematic and implement it, or have someone that works with me do that. And to some extent, we just kind of believe like, okay, this is a tone stack and it has these values of the resistors and capacitors, and you put it in and it kind of does that. And maybe we don't have a Marshall blues breaker to actually compare to, but we're like, well, that's, as long as we think that the schematic is true to the real thing, that's kind of the best that we can do. Now, a source of truth that could be used, if you had a particular one that you were really interested in focusing on, would be to put it into Spice. There's like a software called Spice, or like a example of it is LT Spice. It's a free version of Spice that does circuit simulation, that like will do similar kinds of analyses. It won't allow you to do like real-time audio processing in a plugin the same way that this library would, but that's a tool that's widely used by people that work with circuits to be able to lay out a schematic and be able to analyze it and see how it works, and get some expectation for the way things are supposed to behave. Now, obviously, it'd be cool to have every single one of these circuits, or be able to compare the real hardware to the software and tweak it from there. But trying to build up the quantity of circuits, and have 150 of them, it's just like, hopefully these are just cool effects in and of themselves. If they're close to the real world, that's great. If they're kind of just do something fun and interesting, that I hope can be valuable too.
Okay, great. So another question from Christian K. I'm not going to attempt to pronounce your last name. Sorry. Does it take modulations caused by different analog components into account?
Great question. At the moment, no. I assume the question is somewhat related to like the fact that, you know, if you were to buy a pack of resistors and you have 10 different resistors that are all supposed to be 100 ohm resistors, you're going to get some variation between those. You might have one that's 95 ohms and one that's 101 ohms and one that's 100. And so like, that's just a reality of working with circuits, is like, there's just variation between them. And at the moment, I don't really do anything in the library to like add in some random variation. I've seen some journal articles or heard of some companies that in their own modeling, they will add in some variation to the components to make them, you know, similar to the variation that happens in real audio equipment. But for me, I've just kind of said, if you want a 1K resistor, you get a 1K resistor at this point. But definitely something that I could look at in the future that, you know, could be added in.
Great. Okay, one more question from Studio Devil. How does this library compare to LT Spice and other similar real-time Spice simulations? Live Spice, not LT Spice.
Yeah, so on one hand, I would say like my goal is to make a library that is as accurate and true to like circuit simulation as Spice is. As you know, that's one that's been well adopted and well received and well respected for like a way that if you want to simulate circuits, Spice is a good way to do it. I have geared mine, you know, almost entirely towards people that want to do real-time audio processing, and try to make it very intuitive for being able to do that. Where it's for a software developer that wants to go in and write some C++ code and add a circuit effect to their plugin or to their app and be able to get that analog processing in real time. So, you know, you process at the sample level if you want to, or at the buffer level. And so it's like meant to be easily incorporated into something like a Juice project where, like, I guess with Spice, I don't know, I haven't actually kept up with all the new variations of Spice. But for me, the big limitation of Spice has always been, well, it doesn't really export code, and it's not geared towards just dropping into plugin or some kind of C++ project and being able to get circuit simulation happening right there. It's a great tool, you know, to prototype some stuff and figure out if it is going to work or not, but it's not geared towards that. I guess some people have told me that recently there is some way to do somewhat of some like real-time Spice processing or some real-time Spice thing, which is awesome. I still don't know if it's like meant to be dropped into a C++ project and be able to use that way. But yeah, I think Spice is great. And, you know, I hope that what I'm trying to create for the community of audio software developers is something like, if they're like Spice is like great for getting results of analog circuits, try to get as good of results as Spice, but then also make it like for the audio developer to be able to put into their plugins.
Absolutely. Well, looks like we finally got through all those questions. Wow, that was a lot of great questions. Thank you very much to everybody who took the time to ask them, and everybody who's taken the time to tune in. And once again, if you want to check out the library and some of the awesome resources that Eric has, be sure to check out hackaudio.com. He has a lot of great resources there for people who are looking to get into analog modeling or circuit modeling, DSP, coding. He also has a great book out called Hack Audio, which is about getting started in DSP with MATLAB, but easily portable to other languages like C++. It was a great learning for me going through that book. Yes, thank you very much, Eric. Really awesome.
Thank you.
Cool. And with that, we are going to conclude the audio programmer meetup. Thank you so much to everybody who's tuned in. Normally we do this every second Tuesday of the month, but next month I'm going to make an exception and going to make this the 7th of February rather than the 14th, because 14th is obviously Valentine's Day. There are going to be a lot of people that are going to be out. And so decided to move it back a week. We already have our guests for next month, which I will announce soon. But once again, very exciting. We'll be talking more about some of the exciting things happening in the AI space and also DSP Corner with Rachel Locke, as she'll be back next month. I'm really excited. Thanks to everybody for tuning in. Be sure to join us on the Discord. Once again, that's theaudioprogrammer.com/Discord, and we will see you next time.